A 6.6 kilogram block is pulled to the right across a level surface with a constant velocity by a force of 40 newtons. The force is inclined and horizontal at an angle of 36 degrees. Find mu k, the coefficient of kinetic friction. Again, we have a picture. Again, we're told that this object moves with constant velocity. The force that's pulling it is 40 newtons. We're trying to find mu k. So let's begin again with a free body diagram. Now we're trying to find the coefficient of kinetic friction, mu k. And that's going to be buried in this frictional force over here, because the frictional force is mu times the normal force. So if I could figure out what the normal force is, then I could say the frictional force is equal to the x component of this pulling force. Now I still need to break this pulling force into horizontal and vertical components, but I can do that. Because I know the pulling force is 40 newtons, then I can figure out from the horizontal and vertical components that the horizontal part of the pulling force is 32.4 roughly newtons, and the vertical component is roughly 23.5 newtons. They tell me that the mass of the block is 6.6 kilograms, so I can figure what the weight is. The weight is going to be that times 10, which is 66 newtons. Alright, so I could actually get a number for the normal force. I know that the normal force plus the upward component of the pulling force has got to be equal to the weight, because there's no vertical acceleration. I could put the numbers into this and figure out what the normal force is. And I get that the normal force is equal to 42.49 roughly newtons. Now, horizontally, I know the pulling force, horizontal component, has got to be equal to the frictional force. And that frictional force is mu times the normal force. But I have numerical values for these things now. I know the pulling force is 32.36 newtons. I know that the normal force is 42.49 newtons. I can solve that for the coefficient of friction. So now let me divide the numbers and see what I get. I get that the coefficient of kinetic friction is 0.762. Now my TI-89 calculator has held on to all the decimals, and I've used those. If your number is slightly different, but you've done the same procedure, then that is a correct solution, even though your number may be a little bit different than mine. Linear momentum is defined to be the mass of an object times its velocity. This is a vector quantity. Mass times velocity is equal to linear momentum, which is symbolized by a letter P. This is a lowercase p. You have seen P before in some other contexts, such as pressure and also power. Both of those, pressure and power, are scalar quantities. Momentum with a lowercase p is a vector quantity. Mr. Haynes, why do we care about linear momentum, and why do these physicists always have all these equations that we got to deal with? Well, the short answer is that in May you have an advanced placement physics exam that you're going to take, and you need to know how to do these things because other physicists say that it's important. But in the longer term, the reason is that these quantities have turned out to be useful in trying to analyze and understand and predict and make practical applications to motions of objects. Another reason we're interested in linear momentum is because when Newton wrote his second law of motion originally, he wrote it in terms of linear momentum. So let's think about what Newton's second law says. Acceleration is equal to net force divided by mass. But we also have a definition for acceleration. Acceleration is equal to the change in velocity divided by a time interval, delta v, delta t. Well, you learned in mathematics that two things equal to the same thing are equal to each other. So let's set those two things on the right-hand sides of these two equations equal to each other. And now I'm going to mathematically play with these equations here and do some things that may not seem kosher or legal, but I'm going to kind of wave my hands and argue that I can do them. And let's see what we end up with. First of all, let's start by cross-multiplying both sides. This quantity on the left-hand side, the net force times the time interval, is important enough in physics that it gets its own name, and it also gets its own letter. The letter is the letter J, and the name of this quantity is called impulse. And now I want to wave my hands a little bit. I want to take this mass and I want to associate it with this change in velocity. But I want to bring the mass inside the delta sign. And what I claim is that if the mass doesn't change, then I can say that the mass times the change in velocity is the same thing as the change in the quantity of mass times velocity. Now, why I can say that, I'll be happy to sit down and talk to you about, but just take my word for it right now so we can get through the lecture. And now finally, I want to write down these two things as equal to each other, and I will have what is known as the impulse momentum theorem, and this way of writing it is going to be the most compact way that you'll see it written. You'll notice that on the right-hand side, the mass times velocity, I've substituted p for momentum, linear momentum. What we say is that the impulse is equal to the change in momentum. There are going to be a couple of other ways that you see this impulse momentum theorem written. The way that you'll actually use it will probably be the last way that I write it down. But you ought to see what the others look like just so that when you encounter them in other courses or in other work, then they won't be completely foreign to you. Here's another way you'll see the impulse momentum theorem written down. In this case, what's happened is the quantity of the net force times the time interval is left explicitly, and the change in the momentum is written down as the final momentum minus the initial momentum. You'll also see it written in another way, and this is probably going to be the most common way that you'll use it. I'm going to drop the vector signs and make the assumption that I'm working in one dimension, in which case the sign, S-I-G-N, of the quantities will tell me what the direction is. So implicitly, these are still vector quantities, but I will write it without the vector signs. All three of these ways of writing the impulse momentum theorem, the first way, the second way, and the third way, all mean the same thing. Now, let's talk about some practical consequences of this impulse momentum theorem. We're going to talk about two particular practical consequences. Practical consequence number one, something that you may have heard as an athlete, your coach telling you to follow through. Now, in this application, your coach probably didn't explain to you the theoretical physics that was behind all this, but basically what your coach told you is that if you are striking a ball either with your body or with some instrument, the more that you follow through, in other words, the longer you stay in contact with the ball, the farther the ball is going to go. This means you're exerting a certain net force. So let's say the net force is constant. When you extend the time interval over which that force acts, then you increase the momentum change that that object experiences. So in this case, the net force acting on the object is constant. I extend the time of action and the object's momentum change is increased. This could apply to following through when I'm shooting hoops, basketball. It could apply to following through in the case of rowing or sculling on the water, as in crew. It could deal with kicking a soccer ball, or it might have to do with following through when you're hitting a baseball. I played baseball in college. I wasn't a very good player. I sat on the bench most of the time and kept the books. But there were other players that were excellent. And the coach would tell them to follow through if they wanted to hit a home run. Some of these other good players would also do check swings sometime. In other words, they would start to swing the bat to try to hit the ball, and then they would stop in the middle of that swing and pull back on the bat. If you compare the momentum change of the ball in which the following through occurs, in other words, they're swinging away to hit at the fence, that momentum change of the ball is huge compared to the check swing. And in the check swing, what happens is the ball doesn't really go very far because its momentum change is not as large. So, one practical consequence of the impulse momentum theorem is following through. Another practical consequence has to do with softening the blow or rolling with the punches. This application usually has to do with a collision of some sort. In the collision, the objects that are colliding are usually brought to rest. There is a given momentum change that occurs. It's the momentum change that's constant in this case. Let's take an example of a person who's in an automobile crash. When an airbag deploys, it softens the blow because the amount of time over which the airbag extends the force that stops the person, that force is lessened as a result of that extended time. Here's what we mean by that. Now, at first sight, it may seem these two things are contradictory to each other. In other words, in this second case, I'm extending the time of impact and I'm reducing the impact force, whereas in the first case, I extend the impact time, the time of action, and I increase the object's momentum change. But these two things are actually different because there is something that is different that's constant in both cases. In the second case, the momentum change is what is constant. In the first case, it's the net force that's constant. Let's take a look at what we mean by softening the blow here. And I want to go back to this idea of an automobile collision. I'm a passenger that's traveling in a car. In this automobile, this car is traveling along and suddenly it collides and is brought to a stop. I am a passenger in the automobile who is also going to come to a stop. I have a certain mass. Before the car collides, I have a certain speed. Now, I am an object in motion. So Newton's first law says that I am going to continue in motion until some unbalanced force brings me to a stop. Let's suppose that that unbalanced force is exerted by the dashboard and the windshield. In other words, some very hard object that will exert a force over a very short time interval. That short time interval of action will cause that impact force to be very large. It'll probably injure me. It may even kill me. On the other hand, if I am that same passenger traveling in a car at that same initial speed and I come to a stop, I have the same momentum change, but if an airbag deploys, it will extend the amount of time over which the impact is exerted. That force will be smaller in the case of the airbag than the bone-crushing force of the windshield. Here's what I mean by that in kind of a pictorial sort of way. For a given momentum change, I claim that the thing that's on the left-hand side, the impulse, that includes a large force acting over a very short time interval, can be made equal to a small force acting over a very large time interval. On the left-hand side is what happens when I'm a passenger in a car and I collide with the dashboard. On the right-hand side is my being a passenger in the car colliding with an airbag. I would rather experience the force over a long period of time to make the force small, and I'll be more likely to survive the collision as a result. What I'd like to do is to work a numerical example, and your textbook gives some examples that I think are not as realistic as the one that I've written here. I've written a problem that I would like us to try to solve, and it's an application of the impulse momentum theorem that is this second case that we've been talking about. A 55-kilogram passenger is involved in a collision in an automobile that initially moves at a speed of 45 miles an hour. Compare the collision force the passenger experiences if her non-seat-belted body collides with the hard dashboard and windshield of the car, which brings her to rest in a time of 0.1 microseconds. I want to compare that to the collision force she experiences if her seat-belted body collides with an airbag, bringing her to rest in 50 milliseconds. We want to compare the collision forces with the dashboard and with the airbag. I want to use the impulse momentum theorem to help me. I've got several forms that I could use. The ones that I think are going to be most useful is the one in which I have the information given to me, mass, initial speed, the final speed when she comes to rest in a certain amount of time in one case, and in the other case, I'm going to use the form that shows me force, time interval, mass, and change in speed. Now I'm going to want to work in MKS units and ultimately get forces in newtons. So I'm going to have to convert things that are not in MKS units to things that are. I'm going to work first on the initial speed, 45 miles an hour. And I'm going to use conversion factors to get me to meters per second. I happen to know that there are 1,609 meters in a mile. Many runners might be able to tell you that. That's a good friend to have, in addition to the 1 inch is equal to 2.54 centimeters. But there are 3,600 seconds in an hour. Okay, there's 60 seconds in a minute, and there's 60 minutes in an hour. And 60 squared is 3,600. And the number I get is 20.1125 meters per second. My TI-89 will hold all those decimal places. I'll hang on to them during the intermediate calculations, and then I'll round at the end. The final velocity is 0. I don't need to convert that. Now I've got a couple of time intervals. One time interval, the time interval during which the dashboard exerts its force, is 0.1 microseconds. And the time interval over which the airbag exerts its force is 50 milliseconds. I'm looking for the force, the average force that's going to bring this person to a halt. I'm going to apply the impulse momentum theorem in each case. I'll start with the dashboard case. The mass of the person is 55 kilograms. So I start by solving the equation for the net force that the dashboard exerts. 1.1 rounded times 10 to the 10th newtons. That's 11 billion newtons. That's a lot of force. In other words, when I'm brought to rest by the dashboard, there is a bone-crushing 11 billion, 10 to the 9th, newtons acting on me. Let's try this again with the airbag. We'll start with the same expression for the unbalanced force. And now I'll substitute the numbers in. We'll see that the numerator on this equation is just like the numerator on the other one. The momentum change is the thing that's constant in this case. The thing that's varying is the time interval over which that momentum change acts. 2.2 times 10 to the 4th newtons, 22,000 newtons. And that's a negative number. That negative sign means that the direction of the force is opposite the direction of the initial velocity, which we said was a positive number. So the net force acts in the opposite direction of that initial velocity. 22,000 versus 11 billion. And all as a result of extending the time. I can soften the blow if I extend the time interval. So what we've done in the second part of this lesson is to talk about momentum, to talk about impulse, to write the impulse momentum theorem, and to use it to solve some practical problems and to see how that result can be applied in practical applications. That's it.